Here we consider polytropes. Polytropes are a class of solutions for ideal gases in hydrostatic equilibrium. As a reminder, the hydrostatic equilibrium for a ideal gas is given as grad log P is g, gravity vector, divided by RT. And here we're going to assume that the temperature is not constant. We're not in an isothermal atmosphere, we're in something more general. We need some way to make progress on this because we have two variables, P and T, and we have one equation, the ideal gas, or the hydrostatic balance for an ideal gas. So we need one more assumption. And to do that, we're going to make the following lemma, which is just a fancy way of saying educated guess. We're going to say that there's a polytropic relationship between the pressure and the temperature, or the density and the temperature of the stratified gas. In particular, we're going to say that the density of the gas, normalized to some reference value, rho naught, it is given by a power law relationship to the temperature, T divided by T naught, raised to the power of m. And remember, this is an ideal gas. Which means we immediately know what the pressure is. So P over P naught, well, that's equal to rho R T divided by rho R T at the naught values. We're assuming that R, the gas constant here, is constant. Namely, that the gas is the same everywhere in the atmosphere, the same mixture. And so this is T over T naught now to the m, that comes from our density bit, and then plus 1 since it's multiplied by temperature here. P goes as T to the m plus 1, rho goes as T to the m. M in both of these cases is called the polytropic index, and we'll come back and revisit it shortly. Now, if we take this lemma and we plug it into the hydrostatic equilibrium equation, what we get is that grad log P, well, that, rewriting it using our lemma and using properties of logs of powers, that's m plus 1 times the grad log T, the logarithmic temperature gradient. And the logarithmic temperature gradient, that's just m plus 1 times the gradient of T over T. Now we can take that m plus 1 grad T over T, and this is equal to hydrostatic balance minus G vector, plus G vector over RT. We can cancel the T in the denominator from both sides, and we get the hydrostatic balance for a polytropic ideal gas. M plus 1 grad T is G vector over R, or minus G scalar over R in the z hat direction, and grad T is equal to minus 1 over m plus 1, our polytropic index, m plus 1, times G over R in the z direction. That is our temperature gradient for a polytropically stratified ideal gas atmosphere. Now, there's some nice properties to this. If the gravity is constant, which it is for an atmosphere like the Earth's atmosphere, where we have a large condensed mass underneath us, if the gravity is constant, and if the gas is the same everywhere, so that R is constant, then grad T itself is constant. That's because grad T is G, which is a constant, R, which is a constant, and the adiabatic index in +1, which here is a constant. And not only is it constant, but it's negative, and so T gets colder as you go up. As you go up in the atmosphere, as you increase Z, the T decreases. The gradient is negative. This is actually a decent model for our Earth. The troposphere of the Earth, where we live, where things like rain happen and convection dominates the day-to-day cycle, the troposphere of our Earth has a nearly linear temperature gradient. If we plot the temperature as a function of height, we see that in the troposphere of the Earth, the higher you get, the colder it gets. So here's cold, and here's hot. This is true up to a height of about 10 kilometers. And then above 10 kilometers, different processes take over, and this actually gets hotter again. This is what we call the stratosphere. So named because in this region, the stratification is stable, and then this is the troposphere. Where we live. There's a little person. The stratosphere is where we see gravity waves. It's also where we see things like airplanes, because long-distance airplane flights happen up at about 10 kilometers of height, just in the lower stratosphere. Down here, grad T is roughly constant and less than 0. And the reason that grad T is nearly constant and less than 0 is that the troposphere is well mixed by convection. How are those related? Well, let's think of this M. What is this M? The polytropic index M is given by the grad log density divided by the grad log temperature, and we don't know anything else about it a priori. If, however, if convective processes dominate, and by convective here, we mean convection, the thermal instability, the tendency of hot things to rise, then the adiabatic, or the polytropic index will tend to be the adiabatic index as convection mixes entropy and adiabatically stratifies the atmosphere. And the adiabatic index for an ideal gas is given by 1 divided by gamma minus 1. This gamma here is special to the molecular properties of an ideal gas. And the value of gamma depends on the makeup of the ideal gas. Gamma has a couple of classic values that it's equal to. If it's a monatomic ideal gas, like an ionized plasma, then gamma is equal to 5/3. This is for a monatomic ideal gas. If your gas is composed of diatomic molecules, like molecular hydrogen, or molecular nitrogen, or molecular oxygen, then the value of gamma is 7/5. 7/5. So this is the characteristic value of a diatomic gas. Ideal gas. The difference between these two has to do with the number of degrees of freedom. A monatomic ideal gas has 3 translational degrees of freedom, whereas a diatomic gas adds 2 rotational degrees of freedom, which changes gamma. Now there's one more classically encountered value of gamma that we'll run into relatively often, and this is a gamma of 4/3, and this is a radiation dominated, or as it were, a photon gas. If you know that you have an adiabatically stratified atmosphere and you know what the atmosphere is made up of, whether it's monatomic, diatomic, or photon gas, then you can calculate the temperature gradient for the resulting polytrope. But in all cases, that temperature gradient within the convectively, adiabatically stratified portion of the atmosphere, that temperature gradient will be a constant if the gravity itself is also a constant.